Today we're going to look at polynomial inequalities. So you should know a lot about polynomials now. So we're going to introduce a slightly different idea. So we're going to first look at just polynomial functions. What happens to them when they are being graphed? So maybe like a linear function, for example, or a parabola, or another parabola, or maybe a cubic function. So these are all polynomial functions that we've learned about. Where do each of these functions change sign? So they go from positive y value to negative y value. So what I'm going to do is I'm just going to highlight where the graph changes sign. So all of these values have negative y values, and all of these values have positive y values. So the change in sign is happening right at that point. What about on the parabola? So both of these ends are above the x-axis, so they have positive y values. All of these values down here are below the x-axis, so they have negative y values. Where is the change in sign happening? Right there, going from positive to negative y values, back to positive y values. Does this polynomial function have any change in sign? All the y values up here will be positive. None of my graph happens to be below the x-axis. So sometimes a function may not have a change in sign. And over here, these y values of these coordinates would be negative. Here's my change in sign at 0, and then all of these have positive y value coordinates. So the big idea here is that continuous functions are important in calculus. You will learn a formal definition of continuous functions later, but now all we have to understand is that continuous functions have no breaks in the graph. So when I draw this, I keep my pencil down the whole time and I never pick it up. Same thing over here. Keep my pencil down the whole time, never pick it up. Those are continuous functions. If a function is continuous, like all of these are, it will cross the x-axis if its intercept has odd multiplicity. So all of these x-intercepts had odd multiplicity, right? Because the graph cut through the axis. And when it cuts through the x-axis, it changes sign. It goes from positive to negative or negative to positive. So x-intercepts are key points on the graph of an inequality. So the moral of the story is we should always check our x-intercepts to evaluate inequalities. Now, the inequality has to have one side as 0. So if it doesn't, we could always make one side 0 by adding or subtracting terms to both sides. So the idea of using x-intercepts, vertical asymptotes we're not learning about right now. So the idea of using x-intercepts applies to most of our examples. So there's something that we call a critical number. So a critical number is just the x-intercepts because they are where the graph changes sign. And the test intervals are the numbers between each x-intercept or on the ends of the graph. So for example, up here, a test interval would include this portion of the graph. Another test interval would include this portion of the graph, and another test interval would include this portion of a graph. So this graph actually has 3 test intervals. We would find these 2 x-intercepts, test a value to the left, in between, and to the right. This graph would have no test intervals, so there's nowhere that we would need to test. Either all the answers are positive above 0, or all the answers are negative below 0. And over here, there's only one x-intercept, so you would test this interval to the left of the x-intercept and this interval to the right of the x-intercept. So here's an example. Let's do together. So here is my polynomial. I have 0 on the right-hand side. So my first step is to think of this just as a function. where would the x-intercepts occur? So I'm going to take the quadratic x squared minus 2x minus 3 and just set it equal to 0 and solve for the x-intercepts by factoring. So I think we know that the factors of negative 3 that add up to negative 2 are x minus 3, x plus 1. So my x-intercepts are at positive 3 or negative 1. So this should be a concept that you've already hopefully mastered factoring from our previous unit test. If not, this is going to continue your work on factoring skills. So determine our test intervals. So what I do is I plot them on a number line. So let's see, negative 1 comes before 3 on a number line. The reason I used open circles was because this says strictly less than 0. So I want to use open circles when it says strictly less than 0 because I don't want to include the x-intercept. If this said less than or equal to 0, I could use a filled in circle on the number line. So I have 3 test intervals. I want to know what's going on to the left of negative 1, in between negative 1 and 3, and to the right of positive 3. So now I'm going to test a number inside each of my intervals in the original inequality. So I'm just going to use a different color pen. Give me a number that's kind of a small number that's over here to the left of negative 1. I would choose negative 2. Give me another number that's in between negative 1 and positive 3. I would choose the number 0. And give me another number that's to the right of positive 3. So I would say maybe positive 4. I'm going to test each of these values. These are x values. I'm going to plug them into x and see what I get for y. So if I plug in negative 2, I would get negative 2 times negative 2 is positive 4. And then negative 2 times negative 2 is positive 4 again. And then minus 3. 8 minus 3 is 5. Is 5 less than 0? And I think you would see that the answer is false. So that is not a valid part of our test intervals. When I plug in 0, I'd get 0, 0, negative 3 is less than 0. And you can see that that's true. So this test interval passed. So I want solutions that are in that interval. And then I should test the last interval. So when I plug in 4, 16 minus 2 times 4 minus 3 gives me how much? 8 and 3 is 11. So 16 minus 11 sounds like 5. So is that right? 16 minus 8 minus 3 is 5. All right, so is 5 less than 0? No. So that's another part of our interval that we don't want. So what this tells me is that my solutions for x lie between negative 1 and positive 3, and we're excluding negative 1 because that's an x-intercept, and we're excluding 3 because that's an x-intercept, so I don't put less than or equal to, I put strictly less than. So what this means is, I could have just graphed it, but I'm trying to show you the algebraic method. So if I graphed this parabola and showed you what the graph of it looks like, where is this parabola below 0? Wouldn't you say that this section of the graph is below 0 for all the y values? So it's below the x-axis, and that happens between negative 1 and positive 3 on the x-axis. So all these x values in here produce y values that are negative. So our answer to this inequality is that negative 1 is less than x, which is less than 3, is our final answer. All right, example 2. So this time it's asking you, where is the polynomial x squared minus x minus 6 less than 0? So I start over by trying to find my x-intercepts. X squared minus x minus 6. How does that factor? X minus 3, x plus 2, because negative 3 times 2 is negative 6. Negative 3 plus 2 gives me negative 1. So my two x-intercepts are at 3 or negative 2, right? Because 3 minus 3 is 0, negative 2 plus 2 is 0. So I'm going to plot them on the number line, and I'm strictly less than again, so I'm going to use open circles on my number line. Negative 2 comes before positive 3. So now I'm going to pick my test numbers. So negative 3 falls over there, 0, and maybe 4. So I choose whatever numbers I can that are small so that I can do it in my head. So now I'm going to test my numbers. So if I plug negative 3 up here, I would get 9. Let's see, 9 minus negative 3 minus 6. 12 minus 6 is 6. So is 6 smaller than 0? No. What about if I plug in 0? Is negative 6 on the left-hand side less than 0? And I think you would see that it is. So this time we're going to shade in between our 2 points. And if I try 4, 16 minus 4 minus 6 gives me a total of positive 6 is less than 0, and I think you know that's false. So my solution again is kind of this inner section. Negative 2 is less than x is less than 3. So let's just take a look at this polynomial function here. So we've got x squared minus x minus 6. What does that look like when I graph it? So it's again a concave up parabola. Where was it less than 0? Between negative 2 and positive 3 is where I was below the x-axis. So example 3 is asking us something slightly different. Where is this polynomial function greater than negative 16? So our first step is we need to get 0 on this side. So we're going to add 16 to both sides. And we want to get 2x squared minus 4x minus 16 greater than or equal to 0. So I'm looking for the x-intercepts. Did you notice that you could factor out a greatest common factor of 2 before you start? So I've got 2 times x squared minus 2x minus 8. I'm going to make this equals 0 because I'm looking for the x-intercepts. This is easily factorable as a trinomial now. 2 times x minus 4 times x plus 2, right? Because negative 4 times 2 is negative 8. Negative 4x plus 2x gives me negative 2x. So my x values, my critical values, are positive 4 and negative 2. So I'm going to plot those on the number line. So this time, because it's greater than or equal to 0, I can use a filled-in circle. So I'm going to do a filled-in circle at negative 2 and a filled-in circle at positive 4. I'm going to test negative 3, 0, and 5 as my x values. I'm going to test them in this inequality here because to me that's greater than or equal to 0. So when I plug in negative 3, let's see what I get. I get 2 times 9. Let's see, then this would be, so this is 18, right? 2 times 9. And then I'm actually adding 12 because negative 4 times negative 3 is adding 12. And then I'm subtracting 16. So does that number come out positive or negative? It comes out positive, right? 30 minus 16 is positive, right? Greater than or equal to 0, positive, right? So this section works this time. When I plug in 0, I get negative 16 left on this side. And we know that's not greater than or equal to 0, so it doesn't work. And when I plug in 5, 5 squared is 25. 2 times 25 is 50. minus 20 minus 16, 50 minus 36 is going to come out positive, right? So it would make it true. So this time we have two different solution regions. X can either be less than or equal to -2, or over here, X is greater than or equal to 4. So I have to write two separate inequalities this time, because first I'm over here, then I jump to over here. So you only write one inequality when your situation is a sandwich, like you're in between two values. You write two separate inequalities when you're on either extreme. So before you go and do the guided practice down below, I'd like you to pause the video and try example 4, and then I'm going to walk you through example 4 with my answer, and then I'm going to have you try 5 and 6 and send me a picture of just 5 and 6. So pause the video, try example 4 on your own to see what questions you have, and then I'm going to do the answer. I'm going to show the answer in a minute. So pause the video. So here's my solution to example 4. I found that -5 and -1 were my x-intercepts. I plotted them with open circles on the number line because it was strictly less than 0. I did my 3 test intervals. When I tested -6, I got a positive number, so that was not right. I want a negative number, less than 0. When I tested in between, I got -3, so that section works. And when I tested over here, I got a positive number, so it didn't work. So my final solution was that x has to be between -5 and -1. So please send me a picture of 5 and 6. And just so you notice, number 5 and number 6, your first step is going to be to subtract this number to the left-hand side so that you have 0 over here on the right side before you start factoring and finding your critical values. Thanks, and have a nice day.